Okay, so let's start. So this is the fourth part and final part of the section Dynamics in General Relativity. And yesterday we started to discuss the nonlinear stability towards the future of the Milne model after we extensively discussed the local existence proof and its main ideas. So I just recalled some things we had yesterday already on the board. So the first line, this is the Milne spacetime, where M and gamma, so M gamma is compact, has no boundary, and the metric gamma is a Riemannian Einstein metric of negative Einstein constant -2/9. So Einstein metric, that means that a metric fulfills such an equality with some constant here, and that may be 0, positive, or negative. In our case, it's negative. And then if we evaluate the ADM formalism for this spacetime, we can identify our quantities g, k, tau, n, and x with these values on the right-hand side. Okay? That's just how this model looks like in our formalism. Okay, so what we have here is an expanding space-time. That means towards the future, this expands quadratically in time, t squared times gamma. And we would like to prove stability of this, meaning that if we perturb the initial data slightly, the metric that evolves, that hopefully, and it will, expand, this perturbed metric that will expand should also expand roughly like t squared gamma, yeah? Plus a mild perturbation. So if you have two things that are expanding, to compare them is a bit annoying. So what you do is you rescale the problem. Okay? So if you have something that expands, you just multiply it with something that decays in the right way to obtain something that is essentially constant. Yeah? And what you should multiply it with, naively, if you look at it, so t squared, just multiply it by t to the -2. Then it becomes constant. Yeah? But what we will do is we will rescale it in terms of the mean curvature. So the mean curvature essentially is the time. And we will rescale it in terms of the, so we see here the mean curvature is -3/t. So we will rescale it with tau. So we need to, in this case, multiply the metric g, which is now denotes the perturbed metric. So whenever there is a b, that corresponds to the background. So g again will be the metric corresponding to the perturbation. So we'll multiply it with tau square, and that precisely cancels this prefactor, and we get gamma. So now, just to confuse you a bit, is all quantities so far, so what we've used now, are now denoted by a tilde, yeah? So for instance, g is actually now g tilde. So this is our original variables are tilde because we want to have the non-tilde variables available for our perturbation, yeah? So it's nicer just to change it here instead of writing tilde all the way to the end. So now we define the rescaled variables in the following way. So as I said, g is now tau square times g tilde. The trace-free part of the second fundamental form is tau times the second fundamental form minus tau over 3 g tilde. Yeah? So that's just the trace-free part of the second fundamental form unrescaled. So we rescaled it by tau. The lapse we rescale by tau square, and the shift by tau. Yeah? So there's a physical argument behind this, which corresponds to how these, what are the units of these quantities. If you translate this properly, but for now it's sufficient just to believe that this is the right way to rescale, and for the metric it's obvious. For the shift and depth it's not immediately it's not immediately obvious maybe, but it's sufficient to believe it. And now remember that if we are in mean curvature time, infinity in the future corresponds to tau equal to 0. That's a bit inconvenient because you would like to send your t to infinity, like to analyze a limit. Another thing is that if I would write down the system for these rescaled variables now, I have to transform the system. There's nothing deep behind it. You just have to replace the quantities in the right way. It's just like a calculation. There's no deeper argument behind it. But then there are some explicit time factors remaining in these equations. And you can just do another change of the time variable to eliminate those and obtain a completely autonomous system, meaning that the system only depends on the time and explicitly in terms of the derivative. But there is no explicit time factor somewhere. So it's very nice and elegant. And to obtain that, you define a new time, t by minus ln, tau over tau naught. And in this notation, then minus d by dt is tau d tau. And this is precisely what appears in these equations, in the equations for those quantities. So now you can replace it by a pure derivative. Okay. Tau is the original time of the mean curvature that you used originally. You will not use it. You will just use the d by dt. Tau naught is, that's the initial. Tau naught is the initial tau that you start with. Let's say at tau equal to 1, for instance, or whatever you choose.
Well, I guess in your notation it's like -3 or something like that.
Yeah, exactly. We said yesterday it's -3, but wherever you start with, it will not change anything. So let's start somewhere and fix it and then use that one. But that's correct. To be consistent, that should be -3, what I said yesterday. That's completely right. So now, so this time variable is in R, and t to infinity corresponds to tau from below going to 0. So that's precisely the limit that we're interested in. And in this rescaled formalism, how does the background look like now? So the rescaled GB, that's now also the rescaled, is gamma. Sigma B is 0, NB is 3, and XB is 0. Okay, and what we need to show now So what we need to show is that if we look at the perturbed quantities G, sigma, n, and x, if we look at the difference to the background, this should go to 0 as t goes to infinity. Yeah, that's the aim that we need to show. Why? So that means implicitly that we have global existence in time, but we know that the global existence just depends on the L infinity norm of, let's say, first derivative of these quantities and quantities themselves, but these are certainly bounded by this. So if we see that this decays it certainly will not blow up. Yeah? So that sort of goes without saying, that if we can show something like this, then the data will exist, I mean, the solution will exist for all time, for all time capital T towards the future. Okay. So let's see how the system now looks like in these quantities. So the rescaled system takes the following form. dt of gij equal to 2n sigma ij plus 2 n over 3 minus 1 gij minus the derivative of gij. We can immediately see that if we are in the background where this vanishes and this also vanishes and the x also vanishes, the time derivative vanishes and g stays constant, which is precisely what we would assume, so that's consistent. And now the evolution equation for sigma ij is minus 2 sigma aj, and everybody who sees that already may get excited, because here we see a quantity. If I take a time derivative, it's minus twice the quantity, that looks very much like decay. So this term is essential for getting decay in our estimate. But there will be another relevant term, which is again coming from the spatial curvature. So we will evaluate this term more carefully, getting again a type of generalized Laplace operator. So this is the second important term in this evolution equation. Then we get many terms that are, as we call them sometimes, perturbation terms. So these terms can be roughly estimated and do not really contribute to the structure. So if they would be a bit different, like of having different constants or different signs or something, that would not be a problem. Yes? So I'm already telling you now that the first line is crucial. The second line, you could change the signs if you want. You can like write another term here, third, fourth order. It does not change anything. Just you cannot reduce them in order, yeah, because they need to consist of many products so that they decay and they are smaller than the quantities in with lower exponents, yeah. So if epsilon is small, then epsilon square is even smaller. Therefore, I'm not afraid if these terms would come with some exponent whatsoever. Yeah. Yes, I said that yesterday, but it's up to a constant. It may be 1/2 times this and either it's this or it's 1/2 times that. That is the gauge vector field, so that's essentially 0, but I keep it for didactical purposes because you need this to understand why this combination has a nice expression geometrically. I'll tell you later what precisely the identity is. Okay, so the same is for this. So this would also be 0, of course, but we keep it. So this is the elliptic system. and this is the evolutionary system. And now we know that we are working with CMC foliation. We know we can use the system to say something about our solution. So we can derive estimates for the solution from the system. And now I'm doing something that is also very useful. If you analyze this kind of problems, you make a sort of bootstrap assumption. That means you assume something very rough about the solution, and you prove that you can prove actually much better in the sense of an induction. Yeah? So you can think about it like this. Let's say you have your initial data, and you have a very small perturbation around this initial data. That's what you consider. But now you assume that your solution remains in a large ball, let's say of radius 10, yeah? While your solution is actually of the order 1 over 1,000. But already if you assume that it's in a ball of radius 10, you can bound many quantities very conveniently in your estimates. Yeah? But since you actually show later that you actually remain in a ball of epsilon, you can make a continuous induction argument, which means that your original choice was justified. Yeah? So let's assume we are in a large ball around the initial data. So GK is in BS delta of gamma 0. Yeah? So this delta is, let's say, 1,000 in whatever units. And we make this assumption for now. And that allows us, for instance, to work with the elliptic equations because they, of course, depend also on the solution. So now if the solution is in some sense bounded, then we can really bound our elliptic constants in these estimates just in terms of this delta. So it's very convenient. So the elliptic estimates, what do we get? So first, we get for the perturbation of the lapse an estimate where the constant only depends on delta, where it's important that this is bounded by sigma square. Again, sigma should be small, and sigma square is then even smaller. So this helps us. How do you get this? So first, you apply the maximum principle to this, and you estimate n and L infinity from above and below. You see it's bounded by 3 and 0. Yeah, it's somewhere between. And then you plug this back in and use elliptic regularity just to upgrade your estimates for any order of regularity that you want straightforwardly, because the operator that you get, if you rewrite your equation for an equation to n over 3 minus 1, is nicely elliptic and an isomorphism. Okay, the second estimate that you get is for x, and what we need to just observe here is, of course, I'm getting terms that depend on the n, but then I just plug back in the first estimate, and differences of g and gamma. And you see that if you just if you just observe these terms, you see that every term is at least second order. Either it's n over 3 minus 1, but then you have second order because you're here, or you have products of terms. That's also important because then you get that this actually is bounded by sigma square plus g minus gamma hs square. Yeah, so I'm trying to point out to you these structural features because those are the ones that are really important. While, for instance, as I said, the second line here, you can change, and the precise structure is not so important unless you keep the order of the terms or increase it. Yeah? But the fact that you have squares on the right-hand side here is very important. And now, I tell you another identity that you need to believe, and it's similar to the one that I showed you yesterday, but nevertheless a bit different. If I look at this quantity that appears here on the right-hand side of the evolution equation for sigma, I'm getting, so this is now not the leader derivative, I'm getting that this is actually an elliptic operator plus Gij, where G in Hs minus 1 is smaller or equal C of delta times, I'm writing it here, G minus gamma in hs square. So this is something, again, this is small. You can bound it by a square. That's very nice. The constant times the square of the norm. That's nice. You don't have to worry about this. So this is the principal term of this decomposition. And this operator is now the operator that we had yesterday, that we denoted by G hat. So that was this mixed operator of the background metric and the perturbed metric, minus 2. And I'm getting the Riemann tensor of the background metric, nicely intertwined with my tensor on which I apply this operator, yeah? So it's an elliptic operator minus a 0th order term. Again, this is just the result of a computation. So, before I send the boards down, just let's conclude what we have so far. We know we don't have to worry about the elliptic quantities. By these estimates, they can easily and nicely be bounded by the evolving quantities, K and G, sigma and G. Now, the only question is, how can we derive a nice energy estimate for G and sigma? That's the question. And if we have that estimate, then the perturbative terms in this estimate depend on the elliptic quantities, but they are higher order, so we get something like a nice first order term that shows us that it decays, and then we get a term that we can always bound by the energy to the 3/2, and that's much smaller than the energy itself, and then we can write down the nice decay estimate for the solution. Yeah? Okay, so let's do it, and this will be also the end of, in a sense, the end of this session. Thank you. So again, I will during the day probably I will just put the lecture notes online, and I'm happy for comments and corrections. There's sure a large potential for it, and so don't bother if you didn't manage to copy any of those things here.
The whole board?
Yeah, the whole board. Please. Okay, again, for convenience, I'm using some abbreviations, so to make the equations concise. So U and V should be the quantities that I want to measure. So if I just concentrate on the principal part of the evolution equations, meaning the part that is important, not principal in any other sense, just in the sense that it's important, I'm getting the equations like this. So why am I writing it like this? Actually, so this is just FU and FV are just the terms that I can sort of roughly estimate. And these terms, they would give me a regularity problem, so I have to integrate by parts once. Those terms you can actually just also ignore. They're not so important. The important part is really this part here. Just if you want to do the computations precisely, you need to take care that you can deal with these two terms in an appropriate way. So as I said, we have for F, let's say FU plus FV is an HS minus HS and HS minus 1. This is bounded by C times U plus V s minus 1. Yeah, so these are higher order terms in the good sense. And we discussed yesterday that essentially, or maybe even, no, yesterday, that essentially this is a wave equation for U. We can put in U back in here and we get a wave equation. So the natural energy would sort of correspond to the energy for the wave equation if you would solve a wave equation. So let's write such an energy down. So here I'm writing the operator to the order s minus 1 or s just on the right-hand side. So this scalar product is given by the background metric. I'm just writing it on the right-hand side, or on the right factor. So you can integrate by parts and get a regular energy. That's just a way to write it more conveniently, because otherwise I would have to write many, many terms. So that essentially corresponds to v square and du square and the higher order terms correspondingly. So that's the natural energy for the wave equations with these generalized operators, if you want. Now, if this would be a good, this is very, this is nicely and coercive. So yesterday we learned the word coercive. So there are two important properties of an energy. The first is coercivity. It should really bound the actual norm that we want to estimate, which is the standard Sobolev norm of these perturbations. That's the first thing. The second thing is that it needs to decay. And sometimes you have a problem that the nice energy that is nicely and coercive, that clearly bounds this energy, does not decay at first sight. So let's see what the problem is here. Let's say for the first order, meaning E1, I compute the time derivative of this energy, and what I'm getting is minus 2 v square mu g plus some u, where u is again higher order. So a higher order term can in this sense never be, I'm also careful, but this term is not meaningful. It cannot be used to really get decay or something. Yeah, I'm claiming that here. This term is nice. It's a minus. It's a negative term, but the problem is it just gives me the v term. It does not give me the u term. So it does not give me the full energy. So I want the E1 back on the right-hand side, but I'm not having it. And that's the problem. So this energy seemingly does not really decay nicely. It does not obey a nice decay estimate. And maybe as sort of the last technical lesson from this session on dynamics is there is a beautiful theory, or let's say it's just a try and error thing, I would say, of so-called correcting energy estimates, which means you add diagonal non-definite terms to your energy that may challenge the coercivity. However, they give you very nice decay estimates. And I show you how this works here. So I define the diagonal term ds like this. So that's clearly, it's not clear whether it has no sign in general. And now I define my total energy, EL, as the sum I equal 1 to L of EI plus a constant CE DI. And now there's another bit of analysis that you have to do. So this CE depends on the lowest eigenvalue of this operator evaluated fully in the background. Let's assume that this eigenvalue is strictly bigger than 1 over 9. If it's equally to 1 over 9, it can never be below in 3 dimensions. If it's equally to 1 over 9, you need to decrease this But if you assume that the first non-vanishing eigenvalue of this is bigger than 1 over 9, you can put this to 1. Yeah? Let's stick with this case. I think you're fine with that. And then if I take the time derivative now of the first correction factor, or correction term, d1, I'm getting minus 2 mvu. Okay, that's nice because that's actually just d1. So I'm getting a negative d1 back. That's good. Because if I correct my energy by d1, I also need that on the right-hand side. And then I'm getting a plus v square mu g. Okay, that's bad because that's positive. But here I have two negative ones, so that's still fine. One is cancelled, but there's still one negative remaining. And thank God, I'm getting the minus 9 m Lg gamma u mu g plus v, where v is again a higher order term. Wow, so if I put this together, I'm having here this plus this gives me still a negative term in v. This gives me the negative d1 back, and this gives me the term that I'm missing here. So now it means that this corrected energy fulfills, I'm just writing it on first order, higher order, the computation is of course more difficult. Yeah, so I'm getting something like this. And that means if I, so what I'm getting in general is, okay, maybe I need just a quarter of a board to finish, and it's really just 2 more minutes. So in general, I'm getting dt of Es is smaller or equal minus 2 Es plus c times Es to the 3/2. So if I write square root of Es, if I define y like this, then I'm getting an inequality y dot smaller or equal to minus y plus c y square. And if I put the equality here, just to look at the worst case, and in general it's smaller, so let's look at the worst case, meaning that the case where it's equal, I can, let's say, derive from this that y is essentially bounded up to a uniform constant by e to the minus t. Okay? Thanks. So if I translate this back to my variables, that means g minus gamma in hs plus sigma in hs minus 1 decays like e to the minus t. This is in the rescaled variables. So if I want to get back the physical variables, I need to just do the translation back and just replace all these by the actual quantities. And then I see how fast, in terms of my mean curvature time, for instance, this perturbation decays. And then there's several results, or like one result, for instance, by Choquet-Bruhat and Kotsakis that they showed that if this decay is sufficiently fast in a cosmological spacetime like this, that means that you have geodesic completeness in the time-like sense and the null sense. And that's precisely what we wanted to show. if you want to go back to the rescaled equations, just take a look at those. And remember, actually, so what is the reason for stability of the Milne model? It's the negative sign in front of the sigma on the right-hand side in the sigma equation, there, the minus 2v. It's the first omega v term in du, and it's the Laplacian term, the essential Laplacian term in the dtv equation on the right-hand side. So this structure is precisely giving you the means so that you can construct this energy and show that it decays. All the other terms on the right-hand sides, they could in principle have a different structure as long as they're not decaying slower. Yeah? So this is one proof of a stability. Essentially, it's beside Minkowski stability, the only proof for stability for the Einstein equations with vanishing cosmological constant, as far as I know. There's no, I mean, you know that the Milne model is stable in 3+1 dimensions, and you know that Minkowski is stable. That's the only two results. And here, the nice thing is you can really track down in the structure of the equation where it comes from. So I thank you very much for for your attention. It's very encouraging to see people interested in what you're talking about. You gave me the impression you were interested. I really appreciate this. The papers that are containing all these beautiful ideas, I will put a list on these notes so you can find them and track them down easily. And I'm here for your questions, and if you're interested in more things, please write me an email or something. Thanks a lot, and I'm wishing you all the best for your studies and projects and whatsoever.